Yes.
We are live on YouTube, so probably the show. So I don't know if you can hear me correctly, but welcome everybody. We are there for the PhD defense of TAMIRU Ayalew. The title of the PhD is Automatic Resource Management in Geo-Distributed Multi-Cluster Environment. And this PhD is under the supervision of Professor Guillaume Pierre, Professor Lordson, and Professor Rod. And with different in the jury, we have Professor Liu, Professor Chinoy, Professor Bondik, Professor Yuzup, and myself, Professor Kal. You have 45 minutes for presenting your work, and after we go through some questions for writing the work and
All right.
more information.
Okay, thank you. Can you hear me, everyone?
Yeah, welcome.
Okay. Thank you, everyone, for joining this PhD defense.
There's a switch on the left side.
Yeah,
So,
it's on. Sorry about that. Just a second. All right. Thank you, everyone, to join this defense session of my PhD thesis on automatic resource management in geographically distributed multi-cluster environments. The research work for this thesis was undertaken at the University of Taiwan and the EWISA lab here in France and at Lassis AB in Sweden. So to begin, in our day-to-day lives, we all rely on different online services for work, shopping, entertainment, communication, and the like. And we have high expectations on their quality of service. We want them to be available all the time, reliable and fast and responsive. These applications are provided to us by application service providers who in turn rely on cloud computing for their infrastructure needs. So cloud computing is this paradigm that offers cloud compute infrastructure and services as a utility over the internet, and the users of cloud computing can acquire these resources on demand at any time and pay only for the amount of resources they have used. Therefore, cloud computing offers multiple benefits, such as the flexibility on when and where to acquire resources, the vast amount of resources available, and the outsourcing of the management and maintenance of the infrastructure to cloud service providers. So cloud computing is powered by cloud data centers that are distributed in different parts of the world. These data centers are very large in size and house hundreds and thousands of servers, network equipment, and storage devices. And this allows them to offer their services to a large number of customers who in turn deploy their applications on this infrastructure. The amount of resources allocated to the customers is allocated based on the demand of the customers or the workload that their application receives. Therefore, resource management is of paramount importance in the cloud environment for both the providers and for the users, because we like to improve resource utilization, reduce cost, reduce energy waste, and maximize profits. To this end, we observed two emerging trends in the last few years. The first one is the move towards more and more resource abstraction in the cloud data center to improve resource utilization and automation of resource allocation and application deployment. The second one is a move towards more geographical distribution in order to be closer to end users. So looking closer at the first trend, we see that before the advent of cloud computing, we had this traditional deployment where applications were deployed directly on the physical hardware. This allowed maximum control over the hardware and the software, but sharing this infrastructure among multiple interesting tenants was a problem. Again, porting and migrating of applications from one traditional deployment to another was a problem. Then we have the hardware virtualization technology, which is one of the enablers of cloud computing that allowed to share the underlying infrastructure among multiple tenants who deploy their applications inside virtual machines. And this approach improved resource utilization and portability to some degree. In the last few years, we see the emergence of container technology that improves portability and resource utilization significantly by allowing us to run thousands of applications alongside each other. The applications and their dependencies are packaged together inside self-contained entities called containers. Lately, we see the emergence of container orchestration platforms that automate the lifecycle management of containers and offer additional services such as scheduling, service discovery, autoscaling, and networking. So by abstracting the underlying infrastructure, container orchestration platforms make it easy to consume the cluster or the data center as a single computing unit. Looking closer at the second trend, during the first generation of cloud computing, we had these very large data centers that were often owned by public cloud providers. And then thanks to open source cloud infrastructure management software such as OpenStack, we can achieve hybrid cloud deployments and increase geographical distribution. Lately, we are moving beyond the mega data center model into distributed deployments such as geo-distributed clouds, mobile edge cloud, and fog computing deployments, partly enabled by container technologies. So in the geographical distributed computing environment, we can identify three main computing models. The first one is the hybrid cloud model, where we deploy applications on resources from private as well as public cloud data centers. And some of the motivations for this is achieving low latency, high availability, scalability, and compliance with regulations. In the second multi-cloud model, we deploy applications on resources from multiple cloud providers or multiple data centers of the same cloud provider. In addition to the motivations mentioned earlier, we want to achieve best of breed services and benefit from different pricing models of different cloud providers while remaining vendor neutral. In the third and emerging fog computing model, in addition to the resources from the public cloud and the private cloud environments, we also have resources from micro data centers that are distributed throughout and at the edge of the network. What we want to achieve here is low latency, high bandwidth, and reliable connectivity that is required by some applications in the domains of IoT, video analytics, and virtual reality. So the main questions that we address in this thesis is how we can take these container orchestration platforms that are state-of-the-art resource managers in the cloud now and make them better suited for resource management and application deployment in geo-distributed environments such as hybrid cloud, multi-cloud, and fog computing that are characterized by high degree of distribution, resource heterogeneity, and significant network latency. So in this thesis, we rely on the Kubernetes open source container orchestration platform because it has many desirable features that we want as a building block. First of all, since it's based on container technology, the platform itself and the applications running on it are highly portable from one environment to another. Secondly, it is interoperable with different cloud providers and different systems using standard APIs. Thirdly, by abstracting the underlying heterogeneity and complexity, it presents it through a simple and consistent API that make it easy to use. Next, it is easy to deploy and use the applications on Kubernetes thanks to its simple application model. And lastly, it's highly extensible, allowing us to create additional functionalities in the form of custom resources that can be integrated back to its API. However, it's not easy to use Kubernetes directly in a geographical distributed environment without significant modifications. First of all, since it was designed with a single cluster or data center in mind, its controllers and configurations are not tuned for geo-distributed environments. Secondly, we have to augment it with, for example, the location-aware placement, autoscaling, network routing policies to support different geo-distributed use cases. And lastly, it suffers from significant performance degradation at very large scales. Therefore, in this thesis, we address some of the resource management challenges when trying to use container orchestration platforms in geo-distributed environments, and we propose three contributions. In the first contribution, we look at the problem of using multiple node sizes during cluster autoscaling, and our contribution is an in-depth analysis of the performance evaluation of the Kubernetes cluster autoscaler in a realistic cloud environment using realistic applications and workloads, and we report our results using standard performance autoscaling metrics. In the second contribution, we look at the problem of instability and unavailability that may arise in container orchestration platforms in geo-distributed environments because of bad networking, poor networking conditions, and the static configuration of the control plane. And our second contribution is a feedback controller that improves the stability of the system by adjusting the configuration of the control plane at runtime. In our third contribution, we look at the problem of resource misallocation and under-provisioning that may arise in geo-distributed container orchestration platforms, and we propose a set of controllers with automated placement, autoscaling, and resource provisioning mechanisms to improve the resource utilization. Our contributions were implemented and integrated into the Kubernetes ecosystem and evaluated extensively in realistic test beds. We relied on Kubernetes because of the desirable features we mentioned earlier. However, we think that our contributions can be generalized to other container orchestration platforms as well. In the coming slides, I will focus only on contributions 2 and 3 in the interest of time, and you can read the details of our first contribution in the thesis manuscript. But before, I would like to show you the state of the art in the area of research briefly. So in these slides, I will focus only on those works that are closely related to ours. In the second contribution, we rely on automatic configuration tuning methods to improve the stability of the geo-distributed environment. And in this area, we can group the literature into three groups. The first one is the sampling techniques that help us make sense of the large configuration space that is typical of many distributed systems. And this could be further subdivided into random sampling, divide and divert sampling by Zhu et al. That we have used in our second contribution, and the Latin hypercube sampling technique. And the automatic configuration tuning methods, there are several of them proposed for different types of distributed systems, and we group them into rule-based techniques, machine learning approaches, and optimization techniques. Thirdly, we look at failure detection and recovery works, and this can be grouped into those using timeouts, delay predictors, and control theoretic approaches. Our second contribution is closely related to that of Dessa et al., who propose a control theoretic approach to tune the timeout and monitoring periods of the failure detector in a distributed system in a local area network environment. Similarly, in our second contribution, we use a control theoretic approach to tune the configuration of the control plane, but in a geo-distributed environment. The works related to our third contribution are the geo-distributed container orchestration frameworks, placement methods, and autoscaling methods. Here, we have surveyed a large body of work on the placement of containerized applications in geo-distributed environments, particularly in fog computing environments, and some works on the autoscaling of containerized workloads. the proximity-aware placement and autoscaling techniques by Fans et al. Are of interest, and the frameworks can be subgrouped into those proposed for fog computing environments, IoT environments, and generalized frameworks for hybrid, multi-cloud, and fog. Our third contribution is closely related to seaports by Abdelbaki et al., who propose placement, bursting, and resource provisioning mechanisms using constraint optimization techniques and on Docker containers, but their contribution is not evaluated in a realistic environment. However, our third contribution, in which we propose automated placement, autoscaling, resource provisioning mechanisms, is extensively evaluated in geo-distributed environments. Let's now look into the details of our second contribution, where we try to improve the stability of the geo-distributed environment. In this work, we rely on the Kubernetes Federation framework, that is an extension of Kubernetes for managing multi-cluster environments. And in the high-level architecture shown here, we have the host cluster that hosts the Federation control plane and is responsible for global resource management, monitoring, and placement of applications on multiple clusters that are in turn responsible for placing the user applications and for accepting end-user requests. Kubernetes Federation is interesting for some features such as concepts, template, placement overrides that make it easy to control the placement of applications on multiple clusters. It also introduces abstractions such as federated namespace, deployment, and service that make it easy to conceptualize these multi-cluster applications. However, since it was designed with the assumption of a reliable network connectivity between the host cluster and the member clusters, the configurations are not tuned for geo-distributed environments, and this may lead to undesirable situations, as we will see in the coming slides. So to understand how Kubernetes Federation would perform in a realistic geo-distributed environment, we perform experiments in the Grid 5000 experimental testbed in France, where we have a host cluster or control plane in the Rennes side and 5 workload clusters in Rennes, Nantes, Lille, Grenoble, and Luxembourg sites. Each of the clusters have 1 master node and 5 worker nodes. The table shows 2 of the evaluation scenarios of the networking between the host cluster and the member clusters, and we have here different network latency and packet loss rates. These were based on a recent study by Mohan et al. That we superimposed on the real intercluster latencies in Grid 5000. The application used is a simple Nginx application whose number of replicas are incremented within a short amount of time and submitted to the Kubernetes Federation controller that in turn distributes these replicas evenly across the 5 clusters. So this is the result, the situation in one of the member clusters during the experiment. On the left axis, we have the number of federated deployments indicated using the blue lines, that is updated by the Kubernetes control plane. And the red lines show the number of replicas actually running on that cluster. And the black dashed lines show the desired number of replicas that should have been running on the cluster. And we have this shaded area that shows the areas of instability that is an undesirable situation that we described. And this significant fluctuation leads into undesirable instability and unavailability. And to make sense of this situation, we have the stability metric that captures it using based on the desired number of replicas and the actual number of replicas. Actually, this is the area, the unshaded area under the red curve, but that is normalized across the desirable number of replicas. In the table, we show our results across the entire federation for the average stability. We have 3 experiment scenarios. The stationary scenario where the networking condition is at condition 1 for the entire duration of the experiment. We have the network variable scenario where we increase the network latency and packet loss for 1 out of the 3 hours. And we have a cluster failure scenario where one of the clusters fails permanently for 1 hour out of the 3 hours. And as you can see, the stability is between 83 and 92%, but the optimal value for this is what we expect is 100%. So looking closer at the possible causes of this problem, we see that because of the heterogeneity of networking technologies that can be used between the host cluster and the member clusters that are characterized by high latency and high packet loss rate. And this, coupled with the static configuration of the control plane, leads to premature timeout of control messages from the host cluster to the member clusters. And this leads to reconciliation and health check failures. We also observe false positives during failure detection. As a result, the Kubernetes Federation control plane tries to deploy and remove replicas from the member clusters that have been assumed to have failed. So when trying to address this problem, we have to address a number of challenges associated with it. The first one is how to make sense of the large configuration space in the Kubernetes Federation control plane. And to address this, we use the divide and divert sampling technique to pick the parameter values of the configuration parameters and measure the stability that results from different combinations of the parameter values. And then using principal component analysis, we identify one of the configuration parameters, the cluster health check timeout, to be the one with the most impact on the stability of the system. The next challenge is understanding the trade-off between instability and failure detection delay. And from our experiments, we see that low values of the timeout parameter lead to higher instability, but fast responsiveness to failure. On the other hand, high values of the timeout parameter improve stability, but at the expense of slow failure detection. So from here, we conclude that the timeout parameter has to be kept very low, but not too low to lead into instability. The third challenge is making sense of the impact of the networking environment for a given value of the timeout parameter. And here we see that increasing network latency, packet loss rate, or introducing network failures leads to greater instability for a given value of a timeout parameter. And from this, what we conclude is that we cannot have one optimal value for the timeout parameter. Instead, we have to adjust it according to the network conditions. So based on these findings, we propose a feedback controller that is deployed on the host cluster of the Federation system that continually monitors the Kubernetes controller manager for signs of instability via the error messages collected from the logs. So whenever there are timeout errors observed, it will increase the value of the timeout parameter by a value proportional to the number of error messages. But if there are no changes observed for a predefined consecutive period of time, the value of the timeout parameter is decreased. And we tuned the gain parameters for this controller using the standard Ziegler-Nichols tuning methods. So to measure the performance or the effectiveness of our controller, we performed the same experiment in the same experimental test bed shown earlier. The only difference this time is our feedback controller is running on the control plane of the Kubernetes Federation system. This figure shows the comparison of the uncontrolled case with the controlled case. On the left, we have the stability metric from 0 to 100%, and on the right, we have the value of the timeout parameter. The blue lines show the situation in the uncontrolled case where we have the timeout value fixed into the default 3 seconds. And because of this and because of the poor networking condition, we see significant instability here. On the other hand, the red lines show the situation in the control case where our controller has managed to keep a high degree of instability throughout by adjusting the value of the timeout parameters in each period, and even in the period between 30 seconds and 90 seconds where the network delay and packet loss were increased, still our controller managed to keep high degree of stability. In the tables, we show the average stability across the entire federation. So our controller was able to improve the stability in the range to 99.5 to 100% across the 3 experiment scenarios. So to sum up our second contribution, we showed that Kubernetes Federation-based geo-distributed environments may suffer from significant instability and unavailability because of poor networking conditions and static configurations. And we proposed a feedback controller that managed to improve the stability up to 100% by adjusting the configurations of the control plane at runtime. Let's now look into the details of our third contribution, where we would like to deploy potentially large number of containers across the unified geo-distributed multi-cluster environment while reducing resource disallocation and under-provisioning. In this environment, we rely once again on the Kubernetes Federation system because of 2 desirable features in terms of resource allocation and provisioning. First, it has this manual placement or scheduling capability that helps us to pick the clusters on which we want to deploy replicas on manually. It also has a basic automated placement mechanism where the controller distributes the number of replicas evenly across the selected clusters or based on weights. However, this is not sufficient for a number of use cases in geo-distributed environments, and we have to address a number of challenges. First of all, our platform needs to support different types of use cases in fog, hybrid, and multi-cloud. Therefore, we need appropriate placement, autoscaling policies. Secondly, the clusters are potentially of different capacity. So to avoid resource fragmentation or undesirable situations, we have to have automated placement and offloading mechanisms. We have to also have mechanisms to deal with workload fluctuations. And lastly, if we run out of resources on the fixed clusters, and we may need ways of addressing situations of under-provisioning or dealing with workload spikes. Therefore, once again, to understand how Kubernetes Federation would perform in terms of resource allocation and provisioning in a realistic geo-distributed environment, we perform experiments in Grid 5000 in France, where we have the management cluster in Rennes and the 5 clusters in the other 5 sites. We have 1 master node and 5 worker nodes. For the sake of heterogeneity, 2 of our clusters, 1 and 5, are of greater capacity than the other 3. In the table, we show the network latency in milliseconds between the clusters. It is the inter-cluster latency. And the application used for this experiment is a 1-hour trace of short-running tasks and long-running services modeled after the Google cluster traces. And the CPU request and the memory request distribution is shown here. And these tasks and services are submitted to 1 cluster at a time based on this location information generated using a binomial distribution. In total, we have about 1,100 tasks. So this is the result we get from the experiment. On the left axis, we have the CPU allocation, which is simply the total amount of CPU requested by the pods to be allocated out of the total CPU of the cluster or the entire federation. And on the right, we have the percentage of pending ports, which is simply the total number of pending ports, meaning those that are not running at the moment out of the total deployed ports. And here we see from the solid colored lines that in the out of the 5 clusters, 3 of them are over allocated, or the CPU allocation is more than 100%. And across the entire federation, using the black dashed line, we see that up to twice the total capacity of the federation is over allocated. From the blue dotted lines, we see that the percentage of pending ports reaches up to 65%. So this is because of the absence of automated offloading and resource provisioning mechanisms in Kubernetes Federation. So to address this, we propose a set of controllers under the name of MCKATS that try to address minimized resource misallocation and under provisioning. And now in this slide, I'll show the application model that we would like to achieve in this environment. We start with a number of clusters of potentially different capacity that are distributed in different locations. And the first thing we would like to have is a multi-cluster deployment abstraction that helps us to control the Kubernetes deployment objects that need to be deployed on the selected clusters. The Kubernetes deployment object, in turn, will control the number of replicas that should run on each of the clusters. Next, we have a multi-cluster service abstraction that controls the lifecycle of the Kubernetes service objects that expose the deployments to end-user traffic. After the applications have started receiving traffic, there is most probably workload fluctuation. So to deal with that, we have the multi-cluster horizontal pod autoscaler that adjusts the number of replicas according to the workload received. And if we run out of resources on the fixed clusters, and if we would like to deal to avoid under provisioning or to deal with workload spikes, we may want to add additional resources from a nearby fog provider or cloud provider. So to achieve this, we have the cloud cluster provisioner and autoscaler that transparently provisions a Kubernetes cluster, joins it to the federation so that the deployments and services are extended to the new cluster. If we need to adjust the resources allocated to this cluster, we also have a cluster autoscaler that adjusts the number of worker nodes. And this additional cluster may be removed if it's not needed anymore, again, transparently. In this figure, we show the high-level architecture of our proposed MCKATS and our 4 controllers, namely multi-cluster scheduler, multi-cluster horizontal pod autoscaler, multi-cluster rescheduler, and cloud cluster provisioner and autoscaler, all of which run on the management cluster. In this work, we rely on a number of open source software to give us different services. We rely on Kubernetes Federation to manage the membership of clusters into the federation. We use Cluster API to declaratively create Kubernetes clusters from supported cloud providers. We use Prometheus for resource usage management, such as memory, CPU, and network across the clusters. We use Serve to measure the intercluster network latency. And lastly, we use Cilium for intercluster network routing and load balancing. So the first controller is the multi-cluster scheduler controller that is responsible for the lifecycle of the multi-cluster deployment and service objects. And it supports different manual and automated placement mechanisms. In this slide, I would like to show how it works using a simple example, focusing mainly on the offloading, bursting, and automated placement policies. For the other controllers, I invite you to read the Thesis manuscript. In this example, we have 5 clusters that are located in different places, as you can see, using the intercluster network latency in milliseconds. For the sake of heterogeneity, 2 of these clusters have higher capacity than the other 3. In the first example, we would like to deploy 30 replicas on cluster 2 while offloading is enabled. So our scheduler checks the availability of resources to place 30 replicas on cluster 2, sees that it doesn't have sufficient resources. So next it checks the neighboring clusters and sees that these 4 clusters have sufficient resources. Finally, it selects cluster 2 to offload the 30 replicas because of its proximity to cluster 2. In the next example, we have a request to deploy 20 replicas on cluster 2 while bursting is enabled. Our scheduler checks whether cluster 2 can place all the 20 replicas or some of those replicas and sees that it can place some of the replicas. And for the extra replicas, our scheduler checks the other clusters and sees that they have sufficient resources. So it decides to place 10 replicas on cluster 2 and burst the extra 10 replicas on cluster 1 again because of its proximity. In the next example, we would like to deploy 10 replicas on 3 clusters each using the best fit automated placement policy. Our scheduler checks the entire federation for the availability of resources and sees that 4 clusters have sufficient resources while 1 does not, and picks 3 clusters that are used the most out of the available clusters. In the last example, we would like to deploy 10 replicas using the traffic-aware automated placement policy. So in this case, our scheduler checks the amount of traffic received by the clusters to calculate the number of replicas that should go into each cluster. Also checks the availability of resources to see if those replicas can be placed on those clusters. And finally, distributes the number of replicas proportional to the number of traffic, to the amount of traffic received by the clusters. So to see the effectiveness of our controllers, we perform experiments in the same experimental test bed shown earlier. The only difference now is our controllers are running on the management cluster. Plus, we have an OpenStack cluster to serve as a cloud provider. In the coming slides, I will focus on evaluation scenarios 1 and 3 in the interest of time. So in the first evaluation, this is the results that we get. Again, in the left axis, we have the CPU allocation, and on the right, we have the percentage of pending parts. The solid colored lines show the CPU allocation on each of the clusters, and the black dashed lines show the CPU allocation across the entire federation. So here, because of our controllers offloading capability and because our cluster provisioner provisioned a cloud cluster here at 45 minutes, we managed to keep the CPU allocation under 100%, meaning none of the clusters are over allocated. We also see that from the blue dotted lines that the percentage of pending ports has been significantly reduced. We only see a few pending ports during the time of cluster provisioning and autoscaling, and then they are reduced back to 0. In the third evaluation scenario, we deploy a 2-tier web application with a backend and frontend initially on cluster 2, and we expose the frontend to a workload based on the San Francisco urban taxi traces with significant fluctuation in the workload. This slide shows the situation, the result of the experiment, where we have the number of replicas of the backend application on the clusters, and on the right we see the request per minute of the workload. So from this, we see that our multi-cluster horizontal pod autoscaler starts increasing the number of replicas on cluster 2 in response to the workload. And then when cluster 2 runs out of resources, our scheduler bursts extra replicas to clusters 1, 4, 3, and 5 based on their proximity to cluster 2. And then eventually cloud cluster was provisioned around here at 15 minutes. And the extra replicas were burst there. And thanks to Cilium cluster mesh, the user traffic was routed and load balanced from cluster 2 to the other clusters. Finally, when the workload decreased, our cloud cluster was removed and the replicas of the applications were retracted back to the original cluster 2. So from these results, we see that our controllers managed to keep resource misallocation down and improved resource utilization, even under significant fluctuations in the workloads. So to sum up our third contribution, we showed that the absence of automated placement of loading resource provisioning mechanisms in geo-distributed multi-cluster container orchestration platforms may lead to undesirable resource misallocation and under-provisioning situations. And to address this, we proposed a set of controllers with automated placement, autoscaling, resource provisioning that achieved resource allocation of under 100% and significantly reduced the percentage of pending parts. So in conclusion, in this thesis, we showed that cloud deployments are becoming increasingly geographically distributed, and at the same time, container orchestration platforms have become state-of-the-art resource managers in many environments. However, it's not easy and it's challenging to use them directly in geo-distributed environments. To address some of the challenges that arise, we propose 3 contributions in this thesis. In the first contribution, we offer an in-depth analysis of the experimental evaluation of the Kubernetes cluster autoscaler in a realistic cloud environment. Secondly, in our second contribution, we propose a feedback controller that improves the stability of the system by adjusting the configurations at runtime. And in our third contribution, we propose automated placement, autoscaling, and resource provisioning mechanisms that improve resource utilization in geo-distributed environments. We think that our contributions make Kubernetes Federation better suited for resource management and application deployment in geo-distributed environments by making it more resilient and autonomous. Our contributions were published in the form of 3 papers at 3 systems conferences in CloudCom, Mascots, and ICCN. And the software developed as part of this thesis is made available freely on GitHub. So before closing, I would like to show future possible research directions. First of all, the state-of-the-art container orchestration platform supports our scaling at different levels at the federation, cluster, and application levels. And we have 2 main directions of our scaling, horizontal and vertical. This creates a multi-dimensional autoscaling problem. On top of that, we have the autoscalers having several configuration parameters, making the configuration space very, very complex. So this is an interesting and complex problem worthy of investigating and understanding the optimization of opportunities. In the second direction, we expect geographical distribution of cloud deployments to increase even more in the coming years, and this would introduce potentially different kinds of failures because of the failures of clusters, data centers, network partitions, applications. And we need to come up with ways of proactively detecting failures and recovering from them quickly. In the third direction is in our third contribution, in the management of multi-cluster federated environments, we focused only on placement and horizontal autoscaling mechanisms. However, there are many use cases that require specific placement or autoscaling policies. For example, big data analytics applications may require data locality aware placement, or ultra low latency applications may require priority-based placement mechanisms. So this is also one of the potential research areas. And lastly, the centralized control plane in the federated environment may suffer from single point of failure or performance degradation if we have to manage a large number of clusters. So it is worthy of investigating ways of decentralizing the control plane keeping the performance and the availability of the control plane at optimal value. So with that, I conclude the presentation. Thank you for your attention, and I welcome your questions now.
Thanks a lot. Timing is perfect. So traditionally, we start by question from the reviewers that come the farthest. So I just do a quick check on Google Maps, and it seems that Amsterdam is farther than Vienna. So I would propose that Professor Yusuf, if you can start for the question.
Sure. Thanks for the opportunity. I'm wondering what would happen. I actually live in the south of the country.
Okay.
Anyway, it's still fine. All right. So first, this was a really very nice, very clear presentation. So I'll start with a couple of positives. I think it's always difficult to summarize years of work, and this was a very nice summary. So really polished, really well done. I also like the work overall. One of the things that I appreciate the most is how the candidate has actually combined different, I don't know, even fields or communities of work. Computer systems and control theory, they don't typically see eye to eye. They don't work in the same group, but the candidate has actually combined very nicely techniques from both. I also appreciate a lot the focus on experimental approaches that I like very much, and of course the repeated mention of metrics about elasticity, stability are a plus in my view. But of course, my job is not to only say nice things, also to ask some questions. So I'll try to run the candidate through motivation, problem statement, and then questions about detailed contributions in chapters 4, 5, and 6. And hopefully I will not steal too much time and too many questions from others. So let me start with the question of motivation. First, the simple one. The title includes the term automation. And I get this question a lot. Well, since everything seems to be working already so nicely, why do we need more automation? So why more automation?
All right. So the question is, why do we need more automation? So I think the first motivation is and from the title we have geo-distributed environments, and I said that geo-distributed are one of the characteristics that is a large distribution, potentially thousands or hundreds of thousands of computing nodes that are distributed in different parts of the world. So trying to manage these resources manually is time-consuming, very costly, error-prone. So we need automation at different levels of the management of these resources. So, so the first motivation is we don't have sufficient time, and it is very costly. It leads into errors trying to manage things manually. So we need automation.
So this sounds very reasonable to me. It's also one of the arguments that I'm bringing forth. But on your slide 4, if you could return to it. So
Yeah.
on your slide 4, apparently we already have automation in the first and second generation for multi-cluster geo-distribution. Otherwise, how could the second generation have succeeded?
Yes, that's right.
So
Yeah.
why would you want this automation if it's already there?
So we have automation in some of the systems. So for example, we used Kubernetes as our reference platform for many of our works, and Kubernetes is known for one of its core features is automation. So automating of deployment, automating of service discovery, and so on. But in the geo-distributed multi-cluster environment, so from the works that we have surveyed and from the state of the art, we have noticed that there is a lack of automation at that higher hierarchy of managing global resources globally, and this leads to resource misallocation, resource fragmentation. So we are trying to fill that missing gap, but of course in the layers underneath that there is a lot of automation, and we are also in our work we are basically using that automation. We are not reinventing everything from the ground up.
So I understand, and with this I will end this line of questioning. I understand that Kubernetes doesn't offer this feature, but if I'm looking in your slide 4, I see already 6, 7 icons representing apparently alternatives that do offer this kind of automation, and OpenStack is in the same ballpark as Kubernetes. So isn't the problem already solved? Either this slide is wrong, this separation into generation is wrong, or the motivation seems to be wrong. So I'm trying to figure out which.
So yeah, and the other thing is, so we are trying to use our container technology in this work, and of course OpenStack is famous for managing virtual machines. It may also support managing containerized applications with the help of additional components. But the automation that we need, as again, is at the federation level or at the multi-cluster level. And in the previous generations, for example, in the second generation, to the best of my knowledge, you have to do a lot of engineering work to make this work. It's not available out of the box. For example, from cloud providers. Of course, some cloud providers have their own systems that support this. But yeah, one thing I would like to point out here is that the potential user for the systems that we propose is not a cloud provider or a big company, for example, like Facebook, who have the resources, personnel to allocate to this work to automate this framework. But let's think about a mid-sized company or a small company that acquires resources from multiple cloud providers. And in that case, automation, at least at the federation level, is not given. So you have to work on it. You have to develop some sort of automation at that level.
Mm-hmm. I agree with automation. We are in the same camp here. We like automation. I just think we need good arguments for it. Let me ask a bit about the problem statement. And I'd like you to open slide 24, if you can.
Okay.
Slide 24.
Yes.
So one of the important assumptions about low latency applications and porting them in a more, let's say, cloud continuum or computational continuum, so with resources in the fog and edge, is that the latencies between the resources that are at the edge and the user and the resources that are in the cloud and the user, they have different classes of latency. I think I'm asking this question in a sense for Prashant, who has a very nice article in Supercomputing this year about it. Can you comment what happens when the latencies between users and cloud resources are actually very low, in the range of, I don't know, I see here between 2 and up to 30 milliseconds. What happens with the assumption of we need to go to the edge instead of to the cloud? And how does this change the problem statement in the thesis?
Sorry, could you repeat the question?
I can. If the latencies between users and cloud clusters or clusters located in the clouds are so low as what you measured here, and by the way, I think these are realistic values, are what I've also seen in practice and what Prashant also measured, or his team. When these latencies are so low, what happens with the discussion of we need to go first to the edge for low latency applications?
Okay, so the question is, I think we have now, I think, achieved, especially in North America and Europe, we have several cloud data centers in different regions, and we can already achieve decent amounts of latency. And why do we need the edge when we have that, right? If I understand correctly.
Correct.
Right. So yeah, you're right. I have seen also recent works that show that the original motivations for edge computing, so mainly latency, that was assumed, I think, many years ago, are becoming less and less relevant. One reason is because of the geographical distribution of very large cloud data centers already in North America, in Europe, especially if you use wired connection, you can already achieve latencies of 20 to 40 milliseconds, which is decent for many types of latency sensitive applications. Of course, there are certain classes of latency sensitive applications. Those, I think, are now called ultra low latency sensitive applications, such as video analytics, virtual reality, augmented reality, and the like. I think the choice of choosing the cloud depends on two factors. First is what is the application that you want to run or you want to access with very low latency. Secondly, what is the networking technology that you use? So if you are using a wired connection, I think you can still use the cloud, but if you are use different types of wireless technologies, we still experience significant latency, jitter, and so on. And to add this, a third motivation is bandwidth. So bandwidth, especially at the edge, the network is becoming very congested because of the large amount of data that is generated from sensors, from user devices. So if your application is mission critical, if you cannot handle even a slight disconnection from the network, then I think the edge offers you what you need in terms of So I think these three reasons are main drivers of using the edge.
Okay, I am satisfied with the answer. Let me ask my Mac Kubernetes question. So when you pronounced MCK8S, I compared this with how I read the same term in my own mind. And I read it as Mac Kubernetes. And immediately I associated, of course, the solution with a sort of fast, tasty, rather cheap solution, but not always what it actually promises is true. And of course, you may regret later if you eat there. So my question to you is, which of the promises in your thesis on page 134 does this Mac Kubernetes of yours address, and what are the main regrets that you have at the end of formulating those goals and seeing what you achieved?
Yeah, so yeah, arguing with the name, so Guillaume had the same comments before, so I think we'll change that into a better one later on. So coming back to your question, so in the our objectives for MC KTS was to achieve automated placement policies, autoscaling policies, provisioning, and rescheduling to minimize resource misallocation under provisioning. I think we have addressed most of those, but as you know, in the geo-distributed environments, we have several use cases. For example, in the future work direction, I mentioned ultra-low latency applications, data analytic applications. So right now, we may not be able to support those directly in MC KTS, so we need to work on it more to improve it. The other one is on the rescheduler part. We have achieved the part of rescheduling from the cloud cluster back to the fixed clusters, but it needs more work to reschedule applications that were offloaded to the other fixed clusters in the federation.
In the interest of time, I propose we stop here. I was given a budget of 15. I used like 16. So many thanks for the questions. I'm very satisfied with the answers.
All right, thank you very much for your questions.
Thanks a lot. So I would propose that Professor Oleg, if you can take the next question. She can hear me.
I think she's disconnected. No? Ivona,
Ivona?
it's your time and you're muted.
Oh, sorry, I'm here. I'm here. I can ask question. Is it okay?
Yes, perfectly. Sorry.
Okay. So first of all, thank you very much, Mulugeta, for very nice presentations. I enjoyed it very much. And what I in particular liked about your thesis, and also in presentation, you did the same. You do not just present research questions, you underpin research questions with empirical measurements. So you really measure Kubernetes, and you can say underpinned with numbers what works and what doesn't work. And this is really something very, very valuable in the thesis. I have some questions considering, I would say, methodologies that I would like also to see clarified a little bit. And my first question is, for the first part that you have presented here, so it was the stability measurement and stability management, you have defined a controller. And for the controller design, you used Ziegler-Nicholas method, right?
Yes, yes.
Yeah. So my question is, today, you know, it's almost a good attitude to use machine learning. I mean, you could now implement such a controller using reinforcement learning or Q-learning. So my question is, why did you selected traditional control theory? What is the benefit of this approach, considering and comparing to mainstream, I would say nowadays, which is a kind of data science-driven machine learning approach?
All right. So the question is, why do you use classical control theory instead of modern, for example, learning approaches, right? So yeah, in the second contribution. So what we wanted to do was to start first from understanding the problem, what is really the problem here. And we stated that the problem is poor networking conditions that much of the time we don't have any control on. So the other problem is configuration of the system on which we have control. So we can control it, we can influence it. So we have a lot of solutions to do this. As you said, classical control theory, lots of machine learning approaches, reinforcement learning. So the next question on selecting the solution is, let's start with a simple solution before going to a very complex, the time-consuming approach. Let's start with a simple solution, and that's why we chose the control theoretic approach. So this approach has many advantages. First of all, it's easy to understand. It's easy to implement, easy to tune. It's also explainable. You can explain it, what is going on. If you get some result, you know why that is. You can investigate, you can go back and fix it, and so on. So this simple approach, this simple sources happen to be working for our case. We achieved significant improvements with it. And the other approaches, for example, the modern machine learning approaches, I think this is, I'm speaking here based on my knowledge of the area. I'm not an expert in that area, so I'm stepping out of this. So from my understanding, machine learning approaches, for example, they require collecting a lot of data. So you have to have a lot of historical data. You have to train a model on them, and then you have to continually monitor their accuracy, improve that. So this has a lot of overhead on the management of the control plane. Therefore, since our simple approach has worked, so we did not go to the more sophisticated ways of doing it.
Okay, thank you very much. So you mean the overhead of the method was the main argument?
Yes, that is.
Yeah. Mm-hmm. Okay, good, thank you. The next question that I would like to ask you is about the infrastructure and the middleware you are using. Of course, you have empirical thesis, and I value theoretical and empirical research the same, so both are equally important. What I would like to know is, you have to select now one particular middleware, so you use Kubernetes, right?
Yes.
But is there something that you can generalize for geo-distributed systems here? Is there something that you would say is not particular and not specific to Kubernetes? Because we have also seen, I think Alexandro asked you also about these different generations, and you had also other middlewares on your slides. I think I cannot remember what you had. OpenStack, for example, and so on. So is there something that you can say, okay, that's what I have learned about geo-distributed scheduling, or that's what I have learned about the stability, that is more than middleware?
Yes. So
lessons, it can be also a lesson learned.
Yes. So the question is, how can we generalize our contributions away from Kubernetes? I understand correctly, right?
Yes, yes.
Yeah. So yeah, as I claimed earlier, we think that our contributions can be generalized to other environments as well. So yeah, one of the lessons learned is, no matter the middleware or the underlying resource manager, if you have resources in the large numbers, either in the same data center or located in different data centers or in different regions, you may run into the problem of resource fragmentation or resource entanglement. I think some people call it resource entanglement. That is, some of your resources will be overused, but there are a lot of other resources that are underused. And this creates, for example, problems with running idle many machines, and that results in high power or energy costs. So we want to optimize this. So as much as possible in many areas, for example, many of the big cloud companies, Google, Facebook, and others, they try to manage a large fleet of machines together as much as possible to optimize this problem and to maximize their resource utilization. So one of the main lessons that we learn is the need for a unified management of all the resources that you have, no matter the middleware that you use.
Okay, thank you. Another question that I have is for the placement of replicas. And with this nice picture that you had previously, if you can go also to this picture, I cannot remember which slide it was, where you have this graph between the different clusters.
Is it this one? Or?
Yeah, you just had in the previous discussion with Alexandru. No, where you have these different cluster. Yeah, this one. So what you evaluate here is the placement and how many pods are not allocated at a certain deadline, right?
Yes.
Yes. So my question is, okay, one criteria here and one goal here is to have everything allocated, but what does it mean on a long term, whether the decision was good or bad? Maybe you allocate everything quite fast, but on a long term you have, I don't know, more failures or more customers that are not satisfied. So did you measure a long-term quality of this decision when you run a workload on those allocated applications?
All right. Okay. So the question is, what is the downside of
yes.
allocation?
Yeah.
All right. So yeah, in our contribution.
For example, just one example. Is there maybe a benefit if you put certain group of applications on a same cluster because, I don't know, they have a large data transfers or whatever. Maybe there is a benefit if, for example, certain bunch of application is on the same cluster. So did you evaluate it also that?
So yeah, so this I think would be one limitation of our work. So not evaluated in that regard, but just try to anticipate some of the situations that may arise. So one problem could be, as you said, for example, instead of trying to upload or pass the replicas to other clusters immediately, maybe the user can wait for a few moments, and because they really want that replica to be placed on a specific cluster, so our platform can be extended to support that kind of use case. So to wait a few moments before offloading that replica and to wait until resources are released from that cluster. On the other hand, if we deploy a lot of replicas on the same cluster, so I see one advantage there, that is maximizing the resource utilization. So you can run different types of workloads and share the resources among multiple users or multiple replicas. But on the other hand, as you said, this means that if there are several users that use these applications, and network to that cluster would increase. And The other problem would be potentially some resource interference from the different users of the application. So I think this is one area of limitation of our work that maybe we may need to address this in the future.
Okay, thank you very much. I think that's from my side. I'm, I think, done.
All right, thank you, Ivona.
Thanks a lot. So I would propose that Professor Ling-Yu, yeah, you can start with your questions.
Okay. First, I really appreciate the presentation, and it's a beautiful slides, and also it covers the art and the contribution, and very clearly, and the presenters is also very clearly articulate the problems, the contributions, and the related work. So it's very well done. Also, the thesis seems, and I read, I scanned through. I think it's a very clean and well written also. And I have a couple questions. I will be first starting a question on the geo-distribution orchestration, which is your last part, the third contribution. And I'm going to ask one specific question and then one general question, and then I'll ask a question on the instability. So the specific question here is, you introduce a management cluster that would facilitate the orchestration process across multiple existing clusters, where each cluster has their own auto-scaling capability inside the cluster.
Yes.
So, and then the specific question I have is on two things. One is, and because you are doing horizontal auto-scaling, and then you want to offload certain workload from the busy cluster to a lightweight cluster. So that decision is not an easy decision, because if you based on best fit a policy, and in case your decisions based on the transient behavior, then you may make a wrong decision. So therefore, how to actually making a good balance in the cost of making the decision, and in the correctness of the decision, and in making the offloading process. So that's what I feel is a very difficult problem. So in your design, what would be the policies or decisions you make in dealing with it?
Okay, so the question is, what is the cost of the placement decisions or the bursting decisions? So yeah, so in our placement or auto-scaling, or when we burst, so in our work we support three policies to doing this. So the first one is based on network latency. So we try to burst to the cluster that is closest to the original cluster as possible, and that depends on the availability of resources on that closest cluster. The other ones are based on resource utilization, such as best fit. So we try to offload or burst to those clusters that are the least used, the most used, sorry, or worst fit scenario where we have the least used. So yeah, to be honest, I think this is one area that we did not actually measure any potential downsides that would arise from wrong placement of the replicas on the other clusters. However, we have tried to address this somehow using our rescheduler. For example, if a replica was burst or offloaded into a cloud cluster because of the absence of resources on the first selected cluster, then our scheduler periodically checks this and then tries to reschedule replicas back to their original cluster. But then there is one problem here. So we did not go very deeply into this problem, and this is one limitation of our work, is that this may lead into, for example, if you want to deploy back a replica, it means potentially disrupting of the service of that replica. Therefore, especially this is very problematic if the application is a stateful application or if it is just a single replica of an application. So to make these decisions, we have to analyze what could be affected. So I think this has to be done very carefully. So I think that is one area of limitation of our work.
Okay, thank you. So this leads to a general question in terms of a philosophical question. So in a geo-distributed environment where you have a multiple cluster in a geographically distributed locations, and then what is the philosophy in orchestrate among those set of clusters, even within a single cloud vendor, that they have a different geographically distributed clusters? So because I would imagine some customer, for example, in Austria, doesn't like to share their cluster with people in other places. So therefore, there is a lot of concerns in terms of the data. For example, my data is actually processed within the administrative boundaries. You cannot move my offloading my work to another cluster, which is outside of this geographical distributed policies in terms of where the data should be reside, how to process the data. So there's a lot of philosophical questions in here. And so what do you think in the future, whether this kind of a cross-cluster, cross-geographical distribution boundary type of orchestration is and how this orchestration going to play out in this complex environment, from technical to policy and to privacy related setups.
Okay. So yeah, so the question is away from the technical details, but rather a general understanding of the geo-distributed orchestration or management. So I mean, this is not something that we looked at in this thesis or in our third contribution, but I can speculate some things from based on my understanding. So I think this is a very complex problem from my understanding, especially the issue of data locality, privacy, and so on. Even I think in many countries, for example, in Europe, there is requirement on cloud providers as to the constraints of where they place the user data. If users are from the European region, for example, you cannot place their data in another region. And this is, of course, a very difficult situation with significant implications on the details of the design of resource managers across multiple clusters. And I think this has to be taken into consideration carefully, and the solutions that we provide have to address these constraints very well. So, for example, in the case of placement, if the resource manager should give ways of for the user to specify their desired placement requirements on a high level, in the high level, so they should be able to specify their requirements, and then the resource manager should take those constraints into consideration when making the placement of the replicas in the geo-distributed environment. So yeah, that is my understanding, but it's not something that we looked into details in this work.
Yeah, thank you. Thank you for the answer too. And then the next question actually is related with I see your two contribution, the instability in the geo-distribution multi-cluster and the geo-distribution orchestration are closely related in some ways. And so the next question is related with the second contribution. Can you bring up the slides 13?
Yes.
Yeah, because
this one?
Not this one, 13, yeah, this one. And yeah, I think not really this one, but this is okay. So maybe next one. Can you check on next one? Yeah, maybe it's not. Then it's not I remember wrong. But anyway, so I remember when you have a multiple cluster, you measure their CPU consumptions. And then you have a certain percentage of the pod waiting for resources. And then your decision is improving this kind of wait time, or the amount of pod is being waited. So that is a slide I was trying to well, let's talk about, yeah, something around here, yeah.
Third contribution.
Yeah, and you have a solution slides somewhere. Yeah, but basically, let me just ask a question. I forgot it's not this one, it's another one, but it's related with this one. This kind of a slide. Let's say here. Okay. So basically, when you have multiple clusters, and Kubernetes already have for each cluster they already have this a monitoring capability and an allocation within a auto scaling within the cluster. And then what you have done is to looking at the instability primarily from, for example, health check, timeout, and or some kind of a premature timeout, blah blah. And then so these are actually you're checking it still cluster by cluster, and then try to improve the within each cluster how the health check timeout is set up, and how to reduce the amount of failures, or and increase or reducing the timeout. That's what I see you did. So my question is related with here, which is when you have a predefined health check intervals, or you have a predefined reconciliation issues, and then these kind of policies are defined either by user or by the cluster manager. So then is this easy to actually changing such kind of policies, and especially for the health check timeout, I believe that are also related with a specific type of application, specific type of execution demand, performance demand. So there are many factors that are injected into this application specific, a runtime specific setup. Yeah. So what is a general policy in your experiment? You did a large scale experiment. So then what is the general policy you see from your experience that this kind of periodic monitoring or aperiodic timeout based a monitoring, and that is inadequate. So therefore the opportunity you took to improve it can be significant here. So what is intuition here? That's what I'm interested in learning. And that is one thing related with that. Second thing related with is when you do the health check, actually many cloud research shows that periodic checkout may not be the best way. Maybe you should looking at whether in the previous checkout period, there's nothing happens, then you should not making such a frequent checkout, because those frequent monitoring everywhere can cause the system to have to cause other cases to have the health check failures and things like that. So that's why I said these are very complex matters. So what is the intuition you gain from your experiment?
Okay, so the question is how complicated is the timeout approach? Can it address complicated situations? And the second one is, I think, regarding the monitoring period, if I got this correctly.
Yeah.
So let me start with the first one. So in our second contribution, to remind you, we based our work on the Kubernetes Federation framework. So it is not, we are not dealing with a single Kubernetes cluster. So it is, so to speak, a cluster of clusters. So you have multiple individual clusters of Kubernetes that are independent, autonomous, self-contained. And we have a federation cluster, which itself is a Kubernetes cluster, but is responsible for managing the application placement on these clusters.
Yeah.
So when we try to address the instability problem that arises, we are concerned only about this cluster and not, we are not trying to change, for example, the configuration of each of these clusters. We are only looking at the control plane of the federation host cluster, and that controller has a dedicated control for managing the federation and not its own cluster, but the federation. And in this control plane, we have several parameters. So one of which is a timeout parameter, and there's also a parameter for the monitoring period. So what we do is we try to adjust the timeout parameter of the control plane on the host cluster. On our experiments, we tried to understand this situation using only one application. But from our understanding of that problem, what we find out is that the instability problem that arises is not really related to the applications actually running on these clusters or on the number of applications and so on. Rather, it is because of the poor networking condition and the value of that parameter. And next to that, when we try to adjust the timeout parameter, we are only monitoring the logs from the control plane, and that gives us an indication of the instability problem without going into the details of what applications are running, what is the situation in each of the clusters. So that timeout errors gives us a good approximation or understanding of the problem. So by adjusting the control, the timeout parameter, we can improve the stability. That is what we have found. Trying to understand this problem in a situation where we have many applications with competing that are competing for resources and so on. That is one limitation, I would say, of our work. We did not actually measure that. On the other hand, the second question you raised is, what is the overhead of trying to monitor this repeatedly? And that is a parameter on the control plane, the timeout, sorry, I think it's a monitoring, there is a monitoring period, there is a separate parameter that we did not try to influence, but it is configurable. And by looking at the network usage of the host cluster to the member clusters, if we have, for example, several hundreds or thousands of clusters, obviously the monitoring would create an overhead on the management of the cluster. So that is a concern, but that is not something that we addressed in the second contribution.
Thank you very much for the answer. It's very clear. Thank you, and it's helpful. Thank you. I'm done. Yeah, thank you.
Thanks a lot. So next is Professor Koshanchinori.
Hi, Mulugeta. First of all, let me compliment you also for your very nice thesis. I like the systems aspects of your work, which other committee members have also commented on, the experimental nature of what you did. It's actually very hard to do experimental research, especially if you're doing geo-distributed research. So kudos on all of the work, hard work that you did. I also wanted to say that I like that you have combined your experimental work with using techniques like control theory, which bring a principled view to the problem. So those are all very nice aspects of your thesis, and I did enjoy reading it as well. And I do have a few questions that came out of my reading of your thesis and also your presentation. And the first one is actually related to what Professor Ling was just asking you. This is regarding the chapter where you observed the instability problem, right? So first of all, I mean, it was something I had not seen elsewhere. So it's something that you have found and pointed out, which is great. But I was trying to dig deeper into why there is instability at all. And my questions actually relate to more of the cause rather than your solution. So first of all, I understand that you had an experimental setup where you introduced packet loss and there's network variability, and then you're doing health checks and there's a timeout, and you are seeing instability because of the network variability. And my first question really is more of a clarification. Are the health checks and the requests and results, are they happening over UDP or TCP? Do you know?
I think from my understanding, Kubernetes Federation, it is over TCP.
Okay, because that relates to what I'm going to ask subsequently.
Yeah.
So let's say it's all TCP, right? So then my question is, okay, you introduced packet loss, and I saw that you had 5% loss and 10% loss. And my question is, so what? TCP deals with packet loss quite well. It can retransmit. You have a network link, maybe the round trip times are tens or hundreds milliseconds, say. Your timeout values are 3 seconds or so. Even if you had 5 or 10% loss, you have plenty of time to retransmit, and the health checks should come through to the master or wherever they are going. So if that is the case, if all of the data does make it to wherever they need to be, all the health checks, so why is there instability to begin with? Shouldn't you see that everything is okay, even if there is packet loss or some delays in the system?
Okay, so the question is, why do we observe instability even at the presence of packet loss? So, yeah. So to answer this so we are working with Kubernetes Federation. So the Kubernetes Federation control plane, when trying to place the replicas of the applications, distributing them to the respective member clusters, it periodically checks their status. So whether we have the desired number of replicas running on those clusters. So the way it does this is using the reconciliation control messages and health checks. So the health checks are bounded with the timeout period, and there is also a monitoring period. So that I forgot the default. Every X seconds there is a monitoring, and during that monitoring, control message is sent to the member clusters, and if we have a positive response from the member clusters, then the control plane assumes that that cluster is healthy, so there's nothing to worry about it. But if, for reasons of packet loss, even if there is TCP retransmission, if we hit the timeout period, and if there is a failure, if the control plane detects that the cluster has failed, it will try 2 more times by default. So there is a total of 3 trial times in the control plane. So if all of this fails, then the member cluster is declared as having been failed. So as a result, the controller tries to move the replicas away from that failed cluster to the other clusters. It tries to balance. So as a result, the replicas that were running on the member cluster could be lost. Where, for example, when it tries to come back and join the federation once again.
So maybe you didn't understand my question. You are explaining how the health check triggers a detection of a lost cluster and you do recovery from there. That was not what I was asking. What I was asking is if you're sending all of these messages over TCP, those checks shouldn't fail if the cluster is actually up, because you will, let's say you sent a response to your health check message or the reconciliation message. Maybe the message got lost because you have 5 or 10% packet loss, right? So with 5 to 10% probability, message got lost. TCP takes care of this for you, right? That's the whole reason to use TCP. It is going to detect lost packet and retransmit that packet. And that retransmission will happen fairly quickly, far faster than a few seconds for which you have a timeout interval. So you shouldn't see that at all. The only reason you may actually see it is if those messages were going over UDP, right? It is entirely possible, and this is why I asked you that question, that these checks are happening in UDP, because within a cluster, if you're in a data center, you have high reliability, you may not want to use TCP because it has higher overhead. If this was all happening over UDP, I would agree that higher packet loss should cause this instability. And in that case, I would suggest just switching from UDP to TCP to get around this problem. But if you're claiming that problem is because you're not seeing the responses, TCP should have dealt with that. So I'm not understanding why your federation no control plane is not even seeing responses if you're running over TCP, even with packet loss. This should not be happening. Did you look into this, or do you have understanding of this?
So I think I would have to look into the details of the implementation of Kubernetes Federation. But from my understanding, it's just using a standard HTTP call to see the whether the clusters are alive or not. But yeah, I would have to look into this.
Okay, that's fine. I think I would suggest that you do, because it is good to understand. Your packet losses are not high. If you're seeing 60-70% packet loss, perhaps even with retransmission, you could have seen this problem. But with such low, I shouldn't say low, but I mean, your packet losses are still in 5 to 10% range, so you shouldn't have seen it. So please take a look at it. It may get better understanding of the problem that you're seeing, and might result in better insights.
All right, thank you.
Okay, I have a second question, and this relates to the edge. I think Alexandru asked the question I wanted to ask and stole my thunder, so I'm going to ask a different edge question. And the issue is, if, let's say, there is a lot more edge deployment, just as you see on the cloud, right? There are a lot more regional cloud deployment. We are not sure whether that may happen, because as we were talking about latencies, there's a question of what is edge computing giving you at all. But for now, let's assume that edge computing does become successful, and there are lots and lots of edge clusters. Okay? Now, if you go to a federation model, as you have assumed in your thesis, right, you will have to have the federation control plane manage hundreds or thousands of small edge clusters. Right now, your experiments have gone for 5 clusters that are managed by federation node, if I'm understanding your setup. So my question really is, how well will it scale if you go to thousands? Which chapter of your thesis will actually scale well, and which one will not? Because the assumptions for now are you're trying to deal with the federation of maybe tens of node clusters as opposed to thousands of clusters, which you might see in an edge case. So any thoughts on that?
Yeah. All right. So the question is, how does the multi-clustered federation scales in the orders of large number of edge nodes, right?
Correct.
So, yeah, so in our search contribution, so we relied on the federation model that was using Kubernetes Federation. So we have tried to perform experiments with a few a few federated clusters. But as one limitation is, of course, we did not perform a large-scale evaluation of our work. So that is one area to go into. But some of the things that so from doing that, so I am anticipating that some of the things that need to scale are, for example, placement. When you deal with placement, the algorithms that we used their time complexities are in the orders of the number of clusters. So if we have a large number of clusters, which means the time complexity grows. So that is one consideration of, for example, understanding what is the cutoff for one federation control plane to manage, how many clusters should it manage or not. So that gives us one indication. Also, the other controllers algorithms also should be studied to understand their complexity. And the other thing is, as I indicated, as one potential research area, one problem could be a single point of failure. So the centralized control plane, if it fails for some reason, then of course the applications would continue running on the federated clusters, but you will not be able to deploy additional applications. Other controls such as autoscaling, cloud provisioning would be hampered. So there should be a mechanism to make the control plane either highly available and redundant or following a decentralized approach. So I think one example could be, I have seen a global resource manager by Facebook called Twine. So so they are trying to manage all of their servers across all their data centers. They don't have a single control plane per se, but they have shards of control planes. So a shard is responsible for managing the nodes in one or few regions of their data centers. So I think that is also one approach. So you group a number of edge nodes under a given control plane, and you'd have multiple control planes, and then maybe eventually you'd have an additional layer to aggregate all of this and to have a global view of all the edge infrastructure. So that is my understanding.
Okay, thank you. I think I may be over time, but I'm still going to ask one quick final question. This is what Alexander wanted to ask, and so did I. So what is the chapter of your thesis that was the most challenging and the one that you are the most proud of?
I think I like all of them, but if you force me to choose, I would say the second, I like the stability problem for a couple of reasons. So the first one is we try to explain, to understand the problem as much as possible, but as your question raised, we have to do some further investigation. But before, for example, going into a more sophisticated, more difficult way of trying to solve it, we tried to go step by step, start from a simple way of approaching the problem and see how that solution would perform, and then move to a next one. But a control theoretic approach, which is classical, which is widely used in mechanical systems, electrical systems, and also, of course, in a lot of computer systems, which is easy to understand, but simple, but yet effective, and is also a basis of even the Kubernetes system and other container systems also are based on control theoretic approaches. So I think, yeah, I like that second contribution better than the others.
Great, thank you. Thank you for answering all my questions. I think I'm done with my questions.
All right, thank you, Prashant.
Thanks a lot. So probably we will go to the supervisor now. So I don't know who Johan or Eric want to start.
I can start. So, as being in the role of a co-supervisor, I would like to decline the opportunity to ask questions today. But I anyway would like to take the opportunity to congratulate Mulugeta to having produced a very nice thesis and strong papers in well-established conferences. And in particular, I have enjoyed observing your hands-on approach to research, combining very substantial systems engineering and experimental work with theoretical contributions. And finally, today, I appreciate also the well-organized presentation here, providing a very clear structure of the main contributions over 3 years of hard work. So I would just like to congratulate you to these contributions and leave over to the next.
All right, thank you, Eric.
Thanks a lot, Eric. So I don't know, Johan, if you want to take the opportunity to ask question or give some comment on the PhD.
No, I think that I had plenty of time to ask him questions during the few years. I was very happy to work with him, and I'd like to repeat what Eric said about the very nice experience overall and the great performance today. And from the industrial perspective that I hold working at the Thesis, I'm also very happy to see that the work of Mulugeta has been sort of widely recognized in the industrial community, for example, as being accepted as a talk to the upcoming KubeCon conference, where there's around 25,000 people expected, and Mulugeta made one of the 4 accepted talks that comes from academia. So everyone else is from industry at this big event. So it's very nice to see the applicability of his ideas also in an industrial context. So that's it for me.
All right, thank you, Johan.
Yeah, thanks a lot. Guillaume, if you want to.
Okay, so let me try to get the camera. I'm not sure if I would try to remove my mask, but I'm going to do it anyway.
Yeah, of course.
I'm sorry if this invalidates your business. I hope it doesn't. Just to say, we've gone through a very long journey together because you started your master studies in this university as part of the international program on cloud computing and services. I think it was called at that time.
Yeah.
And you spent 1 year here in Rennes, and then you went for your 2nd year in Berlin. And then I was extremely happy to see when you applied for this PhD position and that you brilliantly obtained the position, and we have the pleasure of keeping on working together.
Yeah.
So it has been a long journey, and I want to emphasize everything that you have done, which is not in the physics. You've worked as part of a European project called FOGRU, which has, well, like every European project, given a few additional workload for reports and whatnot. But what I believe is more important is that as part of these projects, you have been involved in a real-life experiment in Valencia, in Spain, where, well, you did nothing else than to deploy a real fog, to deploy actual sensor devices, to organize a hackathon that allowed, what was it, 63 participants to try those technologies. So you didn't do this alone. This was a teamwork, but I dare say that you were one of the very core members of these efforts. And I really want to thank you for this.
Thank you.
It's been a pleasure to see you grow through those years. You're an incredibly fast learner. I'm really impressed that I don't think I've ever had to give you the same advice twice. In particular, I noticed this while reading your thesis and commenting on the thesis, that every time I made a comment on one piece, somehow automatically that comment was reflected in everything past and future that was to be written in the thesis. And this is not very hard.
It's automation.
It's totally automated. So I'm sure you will keep growing, and I'm really looking forward to this. I have one complaint. Why did you decide to go to industry? such poor taste. So of course you're going to a beautiful company, but nevertheless, I'll conclude by saying maybe my hope, my personal hope, is maybe one day we'll see you back in India. But thanks a lot. It was a really brilliant working together.
All right. Yeah, thank you very much.
Thanks. So I will try to conclude. And so first, I would like to thank you also for the presentation and the quality of the document. I'm the naive of the jury, but I still have some small questions. So I will try to ask you this question. So first, could you? So it's really naive question. So no hesitate to say, okay, we don't care. First, could you come back to the slide 15 or 11, as you prefer? The one where you do the PCA. So you try to optimize the configuration. You do principal component analysis.
Yeah.
And I would like to understand how do you ensure that the different configuration parameters are independent or not? Mm-hmm. Because we could imagine that we have specific interaction between this configuration. So we have a good or bad behavior just because I put this configuration to one, this step, and this. And you will not see that with PC, I guess.
So yeah, what we tried to do was in the second contribution. So when trying to understand what is the impact of the parameters on the stability, so we picked different combinations of parameter values using the sampling technique. Yeah. And we tried to measure the stability. We set up a few minutes of experiment for every combination of parameters, and we obtained a number of results, so about 700 points of results. So we performed principal component analysis, and we identified two of the dimensions that account for the large variance on the impact of the stability. So after that, from that, it's not, of course, clear which of the original parameters have impact. So we use this technique of plotting the biplots that shows the impact of each of the original parameters on the two resulting dimensions. And we saw that on the first dimension that accounts for the largest part of the variance, we saw that on the biplot, the cluster health check time of parameter is the one with the most impact. Okay. So that's why we selected this parameter and continued to influence it.
Great, thanks a lot. Just really a short second question, which is, could you go to 24? We have plenty of questions on this slide, but when you do the presentation, I was a bit,
this one or?
Yeah, sorry, it's this one. I was a bit surprised when you go through this slide that when you do the deployment, it does not go to cluster 4, because you go to cluster 1, and for me, if I got the figures, it seems that the smallest parts regarding the offloading is the one from cluster 2 to cluster 4. No? I don't know if I'm not.
Sorry.
So when you deploy other application, you say, okay, I have to do some burst because I want to deploy another application, and so I decide to go on burst on cluster 1.
Yes.
And I was a bit surprised why it goes to cluster 1.
So cluster 1 is chosen because it is because of this small network latency to cluster 2.
Forget my
2.16.
I'm tired, sorry. Okay, so, and probably it will be my last question because it was a longer question for you. Okay, I come from the application domain, so more about cloud native application, etc. And I'm still wondering when I use Kubernetes and I see such kind of work, why you do not ask more information to the application? Because now when you do DevOps development, etc., you monitor a lot application during the continuous integration stuff, but also during the runtime. So you know, you could have in a way some precise model about resource consumption. And at the end, for doing efficient deployment, you don't really use this information, or you do not ask application to say, not only, of course, she will ask you, I need, I don't know, at least 2 GB of memory or something like that, but you do not have the dynamic behavior of the application, because we could imagine that if you deploy a WordPress, for example, in different instance of your WordPress, depending on the complexity of the domain model, the number of potential user you want that will use this WordPress Explorer, we know really more precisely the CPU, the memory usage, the disk usage, etc., etc. And of course, for open source components, we could have plenty of really precise information about the resource usage by the application. So I'm still wondering why you could not ask this information to the application to say, okay, if you give me this dynamic model about the resource consumption you plan to have, I will provide more efficient deployment.
Okay. So if I understand your question correctly, you are talking about this kind of workflow-based application deployment?
Not only workflow. For me, any application, when you want to deploy it, so you take the example of Index.
Yeah.
At some point, when you deploy Index, depending on the number of users, etc., we know that and depending on the website, the CDN you want to deploy, etc., the resource consumption will not be exactly the same. And and of course, it's a kind of dynamic model, and we have no way in Kubernetes to express this dynamic and to ask this dynamic model to have better deployment strategy.
Yeah. So I think the problem here is that we cannot anticipate what would be, for example, the resource utilization of the application replicas before or at the time of deployment. All we know is how much one replica requires, the quota for that application. But after that, we don't know how exactly. Maybe, of course, as you said, I think you said a model. If we could have a model, perhaps we can anticipate that kind of behavior. But I think in the Kubernetes method and in ours also, we rely on the autoscaling capability of the system. So we just, at the time of deployment, all we want is how much to allocate for a replica, perhaps how many replicas or which placements you want in which regions. But then we would like to adjust the resource allocated based on the traffic received on per region, for example. So in that region, if we receive more replica, more traffic, sorry, we will increase the replicas. Otherwise, we try to adjust that at runtime. But maybe a problem would be sometimes autoscaling would not be as fast as you want it to be to serve your request.
Yeah, no. I agree that autoscaling will not use currently such kind of information, but I'm wondering why we do not go further, because now it's become easier to get this model. So we could imagine not just only to react to say, okay, I need to deploy new instances, but to anticipate that and to, I don't know, specify how we could share this.
I think that's a very interesting point to take into consideration when designing the future resource managers. You have to become more closer to the users. Yeah.
I think I will not. Okay, I have other questions, but I think we already asked you lots of questions. I'm sorry. I think it's really long for you. I would like to ask in the room some PhD want to ask some questions. So if it's not the case, I think we will close the first part of the defense and we will go, I don't know, we remain here.
So Mulugeta and the physical audience can stay in the room, and we will take a few minutes to discuss and come back. For the people online, people on YouTube, so we're going to stop the streaming the video conf. So in particular, François, if you can stop streaming and move to the slide saying that the jury is deliberating. The jury, so Olivia and I will change rooms. And for the online jury, you can disconnect from this video conf and reconnect on the second video conf.
Oliver, you need to unmute.
That's what happens with with physical and software mute buttons. I want to say that I'm not sure if the mute on Guillaume's laptop is intended.
Sorry, I think it's from here.
I will start.
Can you hear us now?
Yes.
Okay,
So
sorry
we have a
about
bit
that.
of echo, I'm sorry. So he has to really set the stuff. I'm sorry about that. So first, thanks for presenting your work today about automatic resource management in geo-distributed multi-cluster environments. So the presentation was pedagogical and polished, and the slides are very nice. And you did an excellent synthesis of your work. The jury really enjoys that you does not only just present the research question, but you underpin each research question with experiment, and you presented this experiment very clearly to motivate your work. So it was really nice to follow and perfectly understand your work. The jury also would like to emphasize the quality of the scientific work and the quality of the empirical evaluation that has been done during this PhD. You combine field from different community, control theory systems, cloud computing, performance engineering, and it leads to excellent contribution. You answer all questions very well, illustrating your excellent knowledge of the fields. And the supervisor has emphasized that the quick learning ability of the candidate, which the evaluator could not assess independently. The jury would like to underpin also the quality of the engineering and the empirical evaluation, which has led to excellent publication in well-established conference. And the mix of theoretical background, computer systems, and control theory is also good for the work unusual. The candidate has mastered all the challenge. So congratulations. So for all these reasons, of course, you got you pass and you will get your diploma, your PhD of University of Rennes. So congratulations.
Thank you very much. Right.
If you want to say something, you
can. Thank you very much. I'm really happy to hear this result. Thank you for thank you, Ivona and Alexandru, to take for taking the time to read the manuscript and to give me your feedback. I would also like to thank the other members of the jury, Ling and Prashant, for being here and for the really nice discussions and for raising very interesting questions. I would like to thank my supervisors, of course, Johan Torsson, Eric Elmroth. I started my research at Elastis AB, which is a company that they set up with a really nice bridge between industry and research. We had really nice discussions at first, and it was very helpful for me to understand my research problems and to start my research. And then I came to Rennes, and once again to work with Guillaume Pierre. I knew Guillaume during my master's studies, as he mentioned earlier, and now during my PhD, he was really very helpful throughout the process of the PhD. He was very encouraging, his feedback, constant feedback, and also when I was writing my thesis, of course, his comments with red pen on the printed thesis manuscript, that was really helpful, and I really thank you, my supervisors. And it was a really great honor for me to work with world-class researchers like Johan, Eric, and Guillaume. Of course, I would also like to thank my friends at the Guru project. We had a really great time together in the past 3 years, despite the difficult situations. I would like to thank my friends and my family, my late parents, Ayalew, TAMIRU, and my mother, Replicas, who was very instrumental in instilling in me the value of hard work and education. So I'm really grateful for them, even though they are not here to share this moment with me. I'm really grateful. I would also like to thank my family. I have a big family, a lot of siblings and nephews, and I really want to thank them all. They have been very supportive throughout my journey. And lastly, I would really like to thank my wife. She's here to this day. She was very loving and understanding and supporting during the last 3 years. So thank you very much. Thank you, everybody. Yeah.
Congratulations.
Thank you.
Congratulations.
So for the online people, we're going to stop the video count and we're going to stop the YouTube. And you're missing the best part, which is the drink. Bye-bye.
All right. Thank
Thanks
you
a
very
lot.
much.
Bye.
Bye.
Bye,
Bye, everyone.
once again.